In this example, we will talk about how many horizontal asymptotes can a function f of x have. We will specifically discuss a case of a function sine of x divided by x and see if this particular function has any horizontal asymptotes. How many horizontal asymptotes can a function y equals f of x have? Well, let's look at the definition of a horizontal asymptote. If we'll look at the behavior of the function f of x as x goes to plus infinity or as x goes to minus infinity, and we notice that the function wants to behave as a constant on either end, then the line y equals b is called a horizontal asymptote of a function y equals f of x. So, how about an example? Y equals square root of absolute value of x. How many horizontal asymptotes does it have? What is the limit of square root of absolute value of x? Well, if x is positive or negative, it really doesn't matter because absolute value of x will always be positive. So as x goes to plus infinity or minus infinity, absolute value of x goes to plus infinity, and square root of plus infinity is infinity, it's not a constant. Therefore, this function does not have any horizontal asymptotes. Next example, y equals 2 plus e to the x. Well, it has only one horizontal asymptote, but how do we know that? If we look at the limit of 2 plus e to the x, as x goes to plus infinity, 2 is always a 2, but e to the x, as x goes to infinity, it explodes. It goes to plus infinity. So 2 plus infinity, it's infinity. It's not a constant. So there is no horizontal asymptote as x goes to plus infinity. But on the other side, as x goes to minus infinity, 2 plus e to the x behaves just as a constant too, because e to minus infinity wants to behave as a constant 0, and 2 plus 0 is just 2. On this graph, you can see the blue line depicting e to the x plus 2, and the green dotted line just below it is our horizontal asymptote y equals 2. So, can a function have two horizontal asymptotes? We actually know a really nice looking function. It's called Arctangent that has two distinct horizontal asymptotes. One horizontal asymptote is y equals pi over 2, and the other one is y equals minus pi over 2. We get pi over 2 when we look at how function arctangent of x behaves as x goes to plus infinity, and arctangent wants to behave as a constant pi over 2. So this is our first horizontal asymptote. If we look at the second limit of a function arctangent of x as x goes to minus infinity, we notice that arctangent wants to behave as a constant minus pi over 2. So the line y equals minus pi over 2 is indeed our second horizontal asymptote. Okay, sneaky question. Can a function of x have 3 distinct horizontal asymptotes? Or 4? 5? 55? No, they cannot. We can only get 2 distinct constants. As a limit of f of x, x going plus infinity can create one constant, therefore creating one horizontal asymptote. And the second limit of f of x as x goes to minus infinity can be equal to the other constant, and this creates the other horizontal asymptote. So the maximum number of horizontal asymptotes for the function f of x is 2. Let's go back to our question. We were talking about a function y equals sine of x over x. We now need to consider 2 limits. What does this function want to behave like when x approaches plus infinity? And what does f of x equals sine of x over x wants to behave like when x goes to minus infinity? We cannot calculate limit of numerator and divide by limit of denominator because neither limit of sine of x or limit of x exists as x goes to plus infinity or minus infinity. Sine of x keeps oscillating between 1 and minus 1. we need something else. And that something else is a sandwich theorem or squeeze theorem. As you notice, sine of x is sort of bounded by two constants, -1 and 1. And if x is positive, what we can do is take and divide all three sides of the inequality by x. This division will not change inequality sign because we're dividing by a positive number. And from the pre-calculus, we know that if we have two constants, a less than b, and we'll take this inequality and divide both sides by the same constant, positive constant x, this division does not change direction of inequality, so a over x is still less or equal than b over x for all positive values of x. If our x is not a positive number, like the case when x goes to -infinity, then we can still create inequality where our function sine of x over x is bounded by the two functions, one from below, one from above. Again, just by dividing by x, creating sine of x over x. -1 divided by x will be there. 1 divided by x is also a function that will be present, but inequality signs have to change because we're dividing by negative numbers. From the pre-calculus, we know that if a is less than b, and we take a constant x, which is negative, then the inequality changes the direction if we either multiply by the negative number or divide by negative number. Therefore, a over x would be greater or equal than b over x. This is it. For the sandwich theorem, we had to come up with two functions, one that binds our function from below and another one that binds it from above. We have two functions, -1 over x and x. So, if we think about the graph sine of x over x, we can graph 1 over x and -1 over x. And 1 over x on the presented graph is identified by the green curves, and -1 over x is purple. So you notice that depending on the case, if x is positive or x is negative, one would bind our sine of x over x from below, while the other function will bind it from above. The beauty of it is such that -1 over x and 1 over x, when x goes to plus infinity, they go to 0, both of them. Therefore, sine of x over x is squeezed in between, and it also goes to 0. By sandwich theorem, limit of sine of x over x as x goes to infinity is equal to 0. We notice very similar observation for the negative values of x as x goes to -infinity, 1 over x goes to 0, -1 over x goes to 0. Therefore, sine of x over x also goes to 0, and we know that the limit of sine of x over x as x goes to -infinity is equal to 0 by sandwich theorem. Now let's talk about horizontal asymptotes. We found the two limits, limit of f of x as x goes to plus infinity, in our case is 0, and limit of f of x as x goes to -infinity, in our case is also 0. This means that we notice how our function sine of x over x behaves. As x goes to either plus infinity or -infinity, f of x wants to behave as a constant 0. Therefore, y equals 0 is a horizontal asymptote. When we're thinking about the graph of a function sine of x over x and the horizontal asymptote that you see drawn in the purple, you notice how our function sine of x over x seems to cross its own horizontal asymptote. Could a function cross its own asymptote? Well, of course it can. Nowhere in definition it says that asymptote can never be crossed. So let's set up sine of x over x equals to y equals 0. And sine of x over x is equal to 0 whenever sine of x is equal to 0, but x is not equal to 0 because we cannot divide by 0. This happens when x is equal to pi or minus pi, 2 pi, minus 2 pi, 3 pi, or minus 3 pi. We can write this as x equals pi k, where k is equal plus or minus 1, plus or minus 2, and so on. So what we just noticed is that our function not only has a horizontal asymptote y equals 0, but it also crosses that horizontal asymptote infinitely many times. So hopefully this will help you to dismiss a common myth that a function can approach its own asymptote but never ever allowed to touch it. Well, that's not quite the case. You just seen an example when it's not only touching its asymptote but crosses it infinitely many times.